For this problem, we're asked the circuit shown has a low pass, impossible to determine, high pass, bandpass, or none of the responses. And if we look at the playlist linked below the like button, there's going to be this video that has high pass versus low pass versus band pass and band reject filters. Mostly we're focusing on high pass, low pass, and band pass here. So this is a filter. If we have an R, or resistor, and a capacitor like this, we know it has to be some kind of filter. So it's definitely not impossible to determine. It's definitely not none of these. And so it has to be either low pass, high pass, or band pass. Now band pass usually has a little bit more to it, and more can be found about this in the notes link below the like button, in the playlist link below the like button. So we're not going to be looking at band pass here. That's not going to be one of our options. So it's either high pass or low pass. Now, a way I like to look at this, and remember this, is that our capacitor, when we have a low response or when we have low frequency, it's going to act as a short, because we know that our impedance of a capacitor is 1 over j omega c. So we basically have 1 over 0, and so 1 over super small number, we're going to go to infinity. And so that's if our omega is small, and then if our omega is big, so we have 1 over j omega c. If it's a huge number, we have 1 over a huge number, that's going to be basically 0. And so with this, we are going to have our current coming in like this. So the current is allowed to pass through here. And then we have this voltage right here, where we have a capacitor across it. Now, I explicitly didn't put the low pass filter on here, because this is what that is. An easy way to also see it, if you don't want to look at this with the actual math behind it, you can say, well, you can remember that low pass, right? Low pass is what we want to look at first. It's the first thing to look at. It's before high pass, right? So we have low pass here. And with low pass, if we were to replace this with an inductor, we have an inductor here and a resistor here. And we can think of this as low, and we have an L on top. But since we have a capacitor, we would just flip this. So the resistor would go here, and our inductor is not an inductor if we have it like this, and it's a capacitor and it goes here. And that's the general kind of form for it. It's not always great to remember the form. You also want to remember how it becomes how it is. And so this is a low pass, but again, it's because we have some current going across this resistor. It's allowed to go across this resistor. And when our capacitor is equal to 0, it's like an open circuit. And when our capacitor is equal to infinity, it's like a short circuit. And so since this is low, it's open, and the current is flowing to the voltage right here. So going back in the video, that is again linked below the like button in the playlist, where we have the RC. It looks just like this. I went back a little bit. We can see that when our omega is equal to 0, which we have here, we act again as an open circuit. You can think of this as, well, it's a 0, so when z of c is equal to 0, we can easily find this. 0 is like an O, so there you have your open, and so obviously this one has to be a short when it goes to infinity. And when it's an open circuit, like we said, we have all this current, it's flowing through here, but it's flowing into the voltage here. So that means the voltage output is going to be equal to our voltage source. Now, when it goes to infinity, capacitor looks like a short circuit, it opens up, and so our voltage output is going to be 0. And that's just a little bit more information. So that's how we would look at this problem and kind of the methodology behind it.